In section 1.4, we're finally going to learn our first technique to solving a very particular type of differential equation, which is called separable equations. And we will end the section talking about various applications that can be used with separable differential equations. So first, let's define what it means for a differential equation to be separable. First of all, we're only considering first order differential equations. And we're supposing that our differential is of the form dy dx, although this would work with any type of differential, and that we have some function on the right-hand side in terms of x and y. We say that this first order DE is separable if you can write it in such a way that you can separate a function g of x on top and f of y on bottom. And then what we're going to do is we're going to take this differential equation and separate the variables. So I'm going to multiply both sides by dx to move the dx over on the right-hand side. And I'm also going to multiply both sides by f of y to move f of y to the other side. That gets us down to this equation where you'll notice that all of the y variables are on the left-hand side. All of the x variables are on the right-hand side. And then once you have separated variables, you can then just integrate both sides. On the left, we're integrating with respect to y, and on the right, we're integrating with respect to x and solve from here. So let's go ahead and practice this approach here of solving a separable differential equation by taking a look at problems 8 and 22 from the textbook. So first of all, for problem 8, what I'm going to do is I am going to move the secant y over to the other side, as well as the dx differential. So that's going to leave me with a 1 over secant y dy equals 2x dx. All right, now keeping in mind that 1 over secant is just the quotient identity for cosine, I'm going to rewrite this as cosine of y dy equals 2x dx. All right, I have successfully separated my variables. I can now integrate both sides with respect to the appropriate differential. The integral of cosine is sine, and the integral of 2x is x squared. Now, these were indefinite integrals, so you need to make sure to include your plus c for a constant of integration. Technically speaking, you could put a c on both sides of the equation, but that would be kind of redundant because we could just move one of those constants of integration over to the other side and combine it with the other constant of integration. So I typically write my constant of integration on the side with the x because I want to explicitly solve for y. But again, it doesn't matter. You could write it on either side. So here, since it's easy enough, I will solve explicitly for y by taking sine inverse of both sides. Make sure that plus c is on the inside of the sine inverse. All right, so here is a solution, or I should say the family of solutions for the differential equation given in problem 8. Problem 22 is similar. The only difference here is that this is an initial value problem. So instead of leaving our final answer in terms of C, we'll want to evaluate and solve for C. So first, let's take a look. I recognize that I actually have two y's on this side. So to start, I'm going to factor a y out. So here's my y. That leaves me with 4x cubed minus 1. And then from here, I'm going to separate. So if I move the y over to the other side, that becomes a 1 over y. And then move the dx differential over. I left a little bit of space to slip in my integration sign. So here's my integral. I have separated variables. Now I'm going to integrate. Very important here on the left-hand side, don't get sloppy when you're integrating 1 over y. Everybody knows it's the natural log function, but it's very important that you include those absolute values. Otherwise, the natural log function is not defined. And again, I'm going to put my plus c over on the x side. So this is going to become an x to the 4th minus x plus c. All right, at this point, we have a couple of different options to solve for your constant of integration. So I'm going to show you two methods. And I'm going to start method 1 right now. Method 1 is going to be to immediately solve for your constant of integration prior to solving explicitly for y. So what I mean here is I'm going to look back up at my initial condition, which I'm highlighting in orange. And if you want, remember, you can write this as an ordered pair. XY is 1 comma negative 3. So what this means is wherever you see an X in your differential equation, you want to replace it with 1. Wherever you see a Y in your differential equation, you want to replace it with negative 3. So I'm going to do exactly that. And here you'll see why those absolute values were necessary. Don't forget them. Okay, so here we have plugged in all of our X and Y values. This becomes the natural log of 3 equals C because our 1's canceled. So we have now solved for C. Let's go ahead and plug that back in to our original solution. And so C is now the natural log of 3. And what we would like to do here is solve explicitly for Y. So to undo that natural log, I'm going to apply the natural exponential function. Remember, it goes to that entire side. All right, so here's where I need you to be very up to par on your exponential properties. So let me change colors here for a moment, and I'm going to write kind of up top. Remember that x to the a plus b is x to the a times x to the b. It is not x to the a plus x to the b. So I don't want to see any of that nonsense over here, okay? So I bring this up because what I see here back down in our solution is an exponential and a natural log. It's not wrong to leave your answer that way, but it's not standard. So it's going to look like you're not very fluent if you're leaving your answer in that way. So what I'm going to do is use that property of exponents to write that as e to the x to the fourth minus x times e to the natural log of 3. All right, so we see that exponential and logarithm cancels out. What I have is the the absolute value of y equals 3 e to the x to the fourth minus x. And lastly, to get rid of that absolute value, remember what the absolute value means. It's positive or it does nothing if your value of y is non-negative, and it negates it if the value of y is negative. So we don't know what the value of y is. It's either positive or negative. So I'm going to write this as y of x equals plus or minus 3e to the x to the fourth minus x. Now, don't leave your final answer with that plus or minus. One of them is correct and one of them is incorrect. And to identify whether you should use the positive or negative, look back up to your initial condition here that I highlighted in orange and just go ahead and impose it. So I'm going to say, okay, well, which is it? Y of 1 has to equal negative 3. And according to what I have written, that is plus or minus 3e to the 1 minus 1. All right, so I know that that exponential goes to 1, and that means I must choose the negative sign here in order for this initial condition to hold. So my final answer is y of x equals negative 3 e to the x to the fourth minus x. All right, and this is your final answer. Now, again, I said I wanted to show you 2 methods of solving for that constant of integration. This was method 1, just evaluating immediately prior to solving explicitly for y. So now let's go ahead and do the second method, all right, which I'm going to start up top here, label it as number 2. Let me rewrite that implicit solution that I just found previously. And rather than solving for C right now, I'm going to solve explicitly for Y. So I'm going to go through this same process of applying the natural exponential function. And then here again, it's kind of your choice as to whether you want to leave the plus C up in the exponential or if you want to bring it out. I tend to bring it out front using, again, that property of exponents. All right, this is a personal preference, but this is standard within differential equations. Instead of leaving this as e to the c, which is itself some constant, I'm just going to kind of abuse notation and rewrite that as c. So I'm going to say, look, c is a constant, so e to the c is another constant. So I'm going to write this as the absolute value of y equals c e to the x to the fourth minus x. All right, and then once more, dropping that absolute value, I need to pay for it with a plus minus sign. All right, so this is as simplified as I can get. Now I'm going to impose that initial condition, y of 1 equals -3. But according to what I have written, that is plus or minus c e to the 1 minus 1, which goes to 1. So in other words, plus or minus c gives me a -3. So now I can write out my answer, y of x equals -3 e to the x to the fourth minus x. And you can see that that got us the exact same answer. What's unique here is what we solve for c. So here I solved that plus or minus c is -3. In method 1, I got c is natural log of 3. So at first glance, you might say, well, those are different, right? Why did we get the same answer? Well, we manipulated our c over here. I'll circle. We recalled e to the c as c, so things got changed a little bit. In this particular example, I prefer method 2. I think that it's a little less redundant in that we didn't have to go back and double check, like, well, should that plus minus be a plus or a minus? It kind of worked itself out. But depending on the type of problem, sometimes I'll do method 1 and sometimes I'll do method 2, just kind of depending on which would be easier in that particular instance. All right, so we've seen 2 examples of how to solve separable equations, one being just a standard DE and the other being one with an initial condition. And we also talked about implicit versus explicit solutions. So let's go ahead and define that formally. We say the equation k of xy equals 0 is an implicit solution of a differential equation if it is satisfied on some interval by some solution y equals y of x of the differential equation. In other words, it's a solution to the DE, but y is not solved for explicitly. So I have an important note that's more of really a warning when you're working with implicit solutions. So first, we're going to suppose that we have an implicit solution k of xy, all right? And then we have some explicit solutions that arrive from that implicit solution. Those explicit solutions may or may not satisfy your original DE. And this entirely depends on your initial condition. So I want to provide you with an example to illustrate how this phenomenon can happen. All right, so consider this differential equation that we have an initial condition as given. An implicit solution of this IVP is given here as the circle of radius 2, right? Let's go ahead and analyze this solution. So first, I want to just verify that this is indeed a solution of this differential equation. So let's verify the solution. Okay, so for this solution here, I just want to check that it does satisfy 2 things. One is the DE, 2 is the initial condition. All right, so what I need for this is I need to double check that x plus y dy dx equals 0. Well, how do I find dy dx? So what I'm going to do is I'm going to take the derivative of this equation and I'm going to solve for dy dx. Okay, so I'm going to differentiate implicitly. This is 2x plus 2y dy dx minus 0 equals 0. All right. And so then what I can do is I can divide both sides by 2. And I'm going to say x plus y dy dx equals 0. And sure enough, yes, that is precisely what that differential equation states. So we know that this is a solution. Let's also double check that the initial condition holds. So the initial condition says that the point xy equals 0, 2 lies on that solution. So let's double check. If x squared plus y squared minus 4 is 0, plugging in what we have, I have 0 squared plus 2 squared minus 4 is 0 plus 4 minus 4, which is indeed 0. So I've now checked both things, that the equation satisfies the DE and also that the equation satisfies the initial condition. All right, so we can now say that this is indeed a solution to the IVP. Let's now take a look at the explicit solutions that it would admit. All right, so what I'm going to do is I'm going to take this implicit solution and I'm going to solve explicitly for y. So like I said, I'll just make a note here. This is just a circle at the origin with radius 2. So when I solve for y, I'm going to get two answers. Y squared equals 4 minus x squared. So when I square root both sides, don't forget that plus or minus. I get the upper semicircle and the lower semicircle. All right, so the question is, are both of these solutions? Now, if you wanted, you could plug it back into the DE to confirm that it does satisfy it. But what I'm going to do is I'm going to check those initial conditions. So I need for y of 0 equals 2 to hold. So that says 2 equals plus or minus the square root of 4 minus 0 squared. So in fact, that's only true if I take the positive solution. The negative solution does not satisfy that initial condition. So what I've just shown here, maybe I'll just write it in red, that y of x equals the positive square root of 4 minus x is a solution. But y of x equals the negative square root of 4 minus x squared is not a solution. And my reasoning is that it doesn't satisfy the initial condition that y of 0 must equal 2. All right, so again, this is just a warning that you can leave your answer implicitly if that is allowed on a given problem. So if the book doesn't specifically say solve explicitly for y, it's fine for you to leave it implicit. But if you're going that extra step to solve for the explicit solution, make sure that you check. If you're getting these plus or minuses, make sure that you check that you're not getting this extra or extraneous solution here. All right, so we have a couple more definitions here at the bottom of page 2. We say that a solution of the differential equation involving an arbitrary constant c is called a general solution. So again, general solution means that you can leave it in terms of your constant of integration. If we're looking for a particular solution, that means you should solve for that initial condition or solve for that constant of integration using the initial condition. And again, definition, a nonlinear first order differential equation may have a general solution involving an arbitrary constant c, as well as one or more particular solutions that cannot be obtained by selecting a value for c. These exceptional solutions are called singular solutions. So what this is saying is we can go through this process of solving the general solution in terms of a constant of integration. But there may be extra solutions that don't arise from that general solution. It's really quite sneaky. Let's look at an example of a DE that admits singular solutions. Right, 32, find a general solution and any singular solutions of the differential equation. Okay, so first of all, this is a singular, or excuse me, a separable DE. So let's go ahead and separate. On the left, I will put all of my y variables. On the right, I only have the dx differential. All right, so moment of truth here. Who remembers the integral of 1 over y times the square root of y squared minus 1? It's something you learned, but it might have been something that you had forgotten. This is secant inverse of the absolute value of y. All right, and then of course there's an understood 1 in front of here. The integral of 1 is x. Tack on your plus c. Okay, let's go ahead and solve explicitly for y here by taking secant of both sides. And then I'm going to pay for that absolute value with a plus or minus. All right, and so this right here is my general solution to the differential equation. Now, I also want to find any singular solutions. So to find your singular solutions, what you're looking for in general, your rule of thumb, is to find constant solutions that satisfy the DE. All right, so we're looking for y equals a constant that satisfies the DE. Now, whenever you have a constant, we know what its derivative is, right? The derivative is going to be 0. So if that's the case, if we know that the left-hand side is going to be 0, then we need only set the right-hand side equal to 0. So if I do that, y square root of y squared minus 1 equals 0, I can set those two factors equal to 0, and I get y equals 0 as well as plus or minus 1. All right. Now, there's an issue here because when I look at this right-hand side here, it's only defined for values of y whose absolute value is larger than 1. Or I should actually say when y squared is larger than 1, but that's equivalent here. So in particular, if I try to plug 0 in to the square root, I get the square root of a negative number. And so I'm going to go ahead and cross off that y equals 0, and my singular solutions are the constant solutions y equals plus or minus 1. All right, again, you can plug those in. On the left-hand side, their derivatives are 0. On the right-hand side, y times the square root of y squared minus 1 is also 0. All right, so these are very sneaky. Again, the rule of thumb should be if you can plug a constant value in on one side and get everything to 0 out, that's a tip off that differential equation is going to have singular solutions. All right, so on that note, let's take a look at this next example here. Or actually, I should say this is the same example, it's just continued. Determine the points A, B in the plane for which the initial value problem as given has A, no solution, B, a unique solution, and C, infinitely many solutions. All right, so what we need to do is we need to think back to the theorem of existence and uniqueness that we learned in the previous section, or maybe it was 2 sections ago. And recall how to go about finding that. So for existence of a solution, remember, we need to be able to find the domain of continuity of our function over here, y times the square root of y squared minus 1 on the right-hand side. And we need to be able to draw a rectangle around our point AB that is contained entirely in that domain of continuity. So let me just make a note here. I'm going to call that function f of xy. So that is y times the square root of y squared minus 1. So where is that function continuous? Okay, the y on the outside can be any value, but what we need here is we need y squared minus 1 to be greater than or equal to 0. Else we're taking a square root of a negative number. So this can then be factored to y plus 1, y minus 1. Oops, and we want it to be greater than or equal to 0. And what I'm going to do here is I'm going to draw a little number line. And I'm going to say, okay, look, I know that the left-hand side is equal to 0 at negative 1 and 1. Let me pick some test points in between. I'll pick 0, 2, and negative 2. And I'm going to plug those values into this left-hand side, and I'm going to see if that satisfies the inequality. So let's start with -2. If I plug in -2, I get 4 minus 1, which is positive, and that satisfies the inequality. And the same is going to be true of 2. Now, if I plug in 0, like we did up above when we had to toss it out, I get negative underneath the square root, and that's bad. Okay? And then what about at plus and minus 1? Plus and minus 1 are okay because that makes that inequality actually equality, 0 and 0. So what I have just discovered here is that the domain of continuity of my function f of xy is the set of points x comma y, so long as y is less than or equal to -1, and I should say, or y is greater than or equal to 1. Right? So here is the domain of continuity. Now here, if you'd like to sketch that on a coordinate axis, you most certainly can. Or maybe grab a different color. Here's y equals 1, y equals -1. Okay, so here's the domain of continuity. Now remember, we want to find where this IVP has no solution. So as long as my point is either above 1 or below -1, I can find that rectangle. But if it's anywhere in between 1 and -1, there's no way that I'm going to be able to find a rectangle. So what I'm going to say here is, since AB is a point with the y coordinate equaling b, then if b is anywhere between -1 and 1, or in other words, if -1 is less than b is less than 1, we cannot guarantee a solution. Okay, so in particular, the differential equation cannot be evaluated there. So this does not exist. Okay, so there is no solution when b is between, -1 and 1. Okay, so when can we guarantee existence and uniqueness? All right, we want both here. Well, we already know that we need b to be greater than 1 or less than -1, but how about uniqueness, right? That's going to guarantee a solution, but not necessarily uniqueness. For uniqueness, if you'll recall, we wanted to analyze the domain of continuity of the partial. So let's find the partial with respect to y. I'm going to have to use the product rule here. So this is 1 times the square root of y squared minus 1. And then, okay, product rule again, or the other half of the product rule, 1/2 y times y squared minus 1 to the -1/2. And chain rule gives me a 2y. So let's see, I can cancel my 1/2 and my 2, and this becomes y squared over the square root of y squared plus 1, and then, minus 1 rather. And then don't forget the initial part, which was the square root of y squared minus 1. Okay, so what I'll notice here is that we already found the domain for the square root piece. That's what we did up above with our number line, that we need to be outside of -1 to 1. However, this denominator now requires us to exclude plus and minus 1. All right. So plus and minus one were in the domain of continuity of f, but they are not in the domain of continuity of the partial of f with respect to y. All right. So as a result now, we need to put dashed lines along here. Those are not included for the domain of continuity of the partial. So here again, as long as we are above the upper dashed line or below the lower dashed line, we're in business. So we have a unique solution for any b values that are in negative infinity to negative 1 open, union open 1 to infinity. All right. That only leaves two b values where we could have infinitely many solutions. And you guessed it, that's going to be when b equals plus or minus 1. All right, why is this true? This is true because these are where the singular solutions occur. So if you think about it, if b is plus or minus 1, we have that automatic solution of our differential equation because when y is plus or minus 1, both sides of the dE equal 0. So it doesn't matter what our a value or our x value is equal to, it will automatically satisfy that dE. So that's why we're getting infinitely many solutions. All right, so we come to the end of the notes here where we want to provide an application of separable differential equations. And this application is probably one that every single person in this class has seen before, but you might not have recognized it as being a differential equation. So we say that the differential equation dx dt equals plus or minus kx, where k is a constant and x is positive. That is the mathematical model for population growth, compound interest, radioactive decay, and drug elimination. So this is called the exponential or natural growth equation. That plus or minus there is just going to identify whether you're growing or decaying. So if it's a growth equation, it's a plus. If it's a decay equation, it's going to be a minus. And I have the solution stated right here, but let's go ahead and derive it. Derivation. All right, let me write out that dE once more, dx dt equals plus or minus kx. All right, and so to separate this, I'm going to take all of the x's on the left. I'm going to leave the t's on the right. Technically, that k can go to either side. So if you wanted to move it to the left, that would be fine. I'm going to leave it on the right. Let's go ahead and integrate. I get the natural log of the absolute value of x equals plus or minus kt plus some constant of integration. I'm just going to make a note here that since we're assuming x is a positive value, we can drop the absolute values. Again, I don't want you to get into a habit of dropping those, so always include them first, and then if you can drop them, that's fine. And then let's solve explicitly for x. So I have x of t equals e to the plus minus kt plus c. Here again, it's not standard to leave your constant up inside the exponential. So if we use our property of exponentials, I can write this as a multiplication of e to the c. And again, it's standard to just rewrite that as c rather than an e to the c. All right, so we have essentially solved for our initial or for our solution. You'll notice the only difference here is that they write that constant as an x naught. That's because what happens if you evaluate x at 0? We get, typically we write that as x naught, and that is c e to the plus minus 0. E to the 0 is 1, so that's c. So we generally write c as x naught. Then we can write our final solution as x of t equals x naught e to the plus minus kt. All right. Here again, that plus or minus is going to depend on whether you're doing growth or decay. So you can choose that plus minus appropriately. So I have a quick note here that says for problems involving carbon dating, you can use the constant K as stated here. So that value is given in the textbook. I'm not going to assume that you have that memorized. If you need to use it on a quiz or an exam, I will provide that constant for you. All right, so let's look at an application of the natural growth equation. Says in a certain culture of bacteria, the number of bacteria increased 6-fold in 10 hours. How long did it take for the population to double? All right, so first of all, how are we going to express this piece of information? That the number of bacteria increased 6-fold in 10 hours. I'm going to let T be the number of hours. Now, this is a decision or a choice that I'm making. If you wanted to do it in terms of minutes, that's fine. You would just need to convert everything. So what this is saying is that our population after 10 hours is 6 times the initial population. So I'm going to express that as 6x naught. All right. And then it says, how long did it take for the population to double? So what is T equal to for the doubling time? So for x of t to equal 2 times the initial population. All right, so here's our setup. Now, we did just derive this solution, but rather than just kind of doing the shortcut and using the solution, I'm going to go through the derivation again. So here again, on a quiz or an exam, I'm certainly not going to give you the solution. Rather, I'm going to give you the differential equation. I'm going to say, recall that bacteria growth is modeled by the equation dx dt equals plus kx in this case, because it's going to be growth. Now, if you happen to have the solution memorized, great, but I'm going to go ahead and just rederive it here. So I have the integral of 1 over x dx equals the integral of k dt. So the natural log of the absolute value of x is kt plus c. Now here, since x is representing the number of bacteria, you can't have a negative number of bacteria. So we know that x is always, well, it could equal 0. I'll say greater than or equal to 0. But in fact, since it's growing, it's not going to be 0. So I guess I'll take away that equality. And so because of that, I can drop those absolute values. And here's where you get to kind of make a choice of how you want to set up your plus c. I'm going to go ahead and apply the exponential function. So that's e to the kt plus c, which is e to the kt times e to the c. Or like we said previously, I can write that as x naught e to the kt. All right, so now I'm going to use my initial condition here. And it says that when t is 10, I get 6 times the initial population. So that's x naught e to the 10k. Since we can't start with 0 bacteria, otherwise it wouldn't grow, I know that x naught is non-zero, so I can divide both sides by it. I have 6 equals e to the 10k. So I have the natural log of 6 is 10k, or k equals the natural log of 6 over 10. All right, now I really want you guys to refrain from pulling out your calculator. So I'm just going to make a note. Don't approximate this. Don't punch it in your calculator and get some hideous decimal out, because you're going to have to round and your answer is no longer going to be exact. So instead of that, what I'd like you to do is just plug k in exactly as I have it written. If you want to write it as 1/10 natural log of 6, that's fine as well. So let me go back up to my x of t, and I'm going to say x of t is equal to x naught e to the, and instead of k, I'm going to write 1/10 natural log of 6 t. And I'm writing those parentheses so that you don't think that the t is inside the natural log. It is not. All right, finally, I want to solve for t so that my population is double the initial. So what I'm going to do is I'm going to equate this to 2x naught. Here again, x naught is non-zero, so I can divide both sides by it. And what I have is e to the 1/10 natural log of 6 t equals 2. So we need only solve this equation for t, and we're finished. So I have 1/10 natural log of 6 times t equals the natural log of 2. So t equals the natural log of 2 divided by 1/10 the natural log of 6. All right, at this point, this is when you can finally pull out your calculator. Up to this point, you should not have even accessed it. And then here, I'm going to round to 2 decimal places. This comes out to approximately 3.87 hours for the bacteria to double from its initial population. All right, we're going to end these notes here with one last example, and it's going to be Newton's law of cooling. So let's take a look at that. So I have a remark here. Newton's law of cooling states that the time rate of change of a temperature, capital T of T, of a body immersed in a medium of constant temperature A is proportional to the difference A minus T. Remember, we discussed when we talked about mathematical modeling, is proportional to gives the equals K times. So don't forget that K when you're setting up proportions, and then that difference A minus T. Here, we made a note that K is always positive. All right, again, I don't want you to memorize this differential equation. If I say use Newton's law of cooling to solve the problem, then I will also provide you Newton's law of cooling. All right, so let's take a look at an example here using Newton's law of cooling. A cake is removed from an oven at 210 degrees Fahrenheit. So this is our initial temperature. The temperature at time 0 is 210 degrees Fahrenheit. And it's left to cool at room temperature, which is 70 degrees Fahrenheit. So remember, the constant temperature A is 70 degrees. Okay. Says after 30 minutes, the temperature of the cake is 140 degrees Fahrenheit. When will it be 100 degrees Fahrenheit? All right, so at this point, you need to make a decision. Do you want time to represent minutes or hours? If it's minutes, you can write this as T of 30. If it's hours, it's going to be T of 1/2. So I'm going to let T be given in minutes. But again, just make that choice. And if that's the case, then I know the temperature after 30 minutes is 140 degrees. And the question is, what time will it be in order for the temperature of the cake to decrease to 140 degrees Fahrenheit? Okay, so first, I'm going to make a quick note here. What's something that I know about the temperature of this cake? I know that it's starting off at 210 and it's cooling down. And furthermore, I know that at least on planet Earth, it's never going to get below the temperature of the room, right? It's not going to spontaneously get cooler than 70 degrees. All right, so what that tells me is that the expression A minus T, where A is 70, that is always going to be, see, in this case, less than or equal to 0, right? At first it starts at 210 degrees and then it's lowering and it's lowering, but it's never going to get below 70. So in other words, I can write this as 70 minus T is always negative. Okay, so what I'm going to do here is I am going to set up my Newton's law of cooling. I have d capital T, d lowercase t is K, some constant, times 70 minus T. Now let's go ahead and separate variables. I have the integral of dt over 70 minus t is equaling the integral of k d little t. So let's go ahead and evaluate, or I should say integrate. I have the natural log of the absolute value of 70 minus t equals kt plus c. So here again, those absolute values are actually very important because we just noted that 70 minus t is always going to be a negative value, or at least 0 or negative, should say non-positive. So now what I'd like to do is I would like to probably solve explicitly first, although again, you guys can kind of choose whether you want to solve for c now or later. So this is going to be e to the kt plus c. I'm going to go ahead and write this as c e to the kt. And then I'm going to recognize here that oh my goodness, one thing here. Let me write this in red. In order to integrate this, if you did a u substitution, your du dt would actually pop out a -1. So as a result, I need to be sure to include that negative sign right here. And I was being hasty and left it out. So I'm adding that in here in red. And so if I divide that over to the other side, that's going to become a negative up top here. So I'm just going to add that in red. Make sure to edit your notes there. All right, so now what I had mentioned was, since 70 minus t is indeed less than or equal to 0, I need to pay for that absolute value here with a negative sign. So I'm going to do that now. So this is negative 70 minus t equals c e to the negative kt. So in other words, t minus 70 equals c e to the negative kt. All right, so finally I can add that 70 over, and I have my general solution. T of t is 70 plus c e to the negative kt. All right, so now let's look back up to our initial conditions here. I have the temperature at time 0. T of 0 is 210. So that would be 70 plus c e to the 0. So in other words here, we're able to solve for c. C is going to equal 140. So c is 210 minus 70, 140. All right, so let's plug that in. T of t is 70 plus 140 e to the negative kt. We were able to solve for c, but we have not yet solved for k. So to solve for k, we're going to use our other initial condition that T of 30 was 140 degrees. So let's go ahead and plug in 30 for little t. I'm going to subtract 70 from both sides. Divide by 140. Apply the natural log function. And lastly, solve for k. So k is negative 1/30 of the natural log of 1/2. Here again, resist the urge to plug this into your calculator. Rather, leave it as an exact answer so that you're not rounding anywhere. So coming back up here to our T of t function, I'm going to plug that in for k. So 70 plus 140 e to the, I have a double negative, so that's going to make this a positive 1/30 natural log of 1/2. And then I still have my t on the outside. All right, so this is our particular solution at this point. And now we can do our final step, which is to find when the temperature is going to be exactly 100 degrees. So I'm going to set T of t equal to 100, and I need only solve for t. Okay, so if I subtract 70 over, that gives me 30, and divide by 140 gives me 3/14 with this nasty exponent. Apply the natural log to both sides. And then finally divide through by that expression. So I have t equals the natural log of 3/14 divided by 1/30 natural log of 1/2. And so here again, this is where you can finally pull out your calculator. Recall what we chose for our units of T. We had chosen minutes, so make sure that you include that label in your final answer. And this comes out to approximately 66.7 minutes for that cake to cool down to 100 degrees Fahrenheit. All right, this concludes our notes on separable equations and their applications. And next up in section 1.5, we're going to learn how to solve differential equations that are known as linear first order equations.